Hello and welcome to another computational geometry video. Today we're going to be discussing the more of what we were talking about last time, but this time I have it in order. We're going to discuss the less than perfect examples. Last time I was having a little bit of trouble remembering exactly how we constructed the wide stars, which are examples of non-Homestead polygons. In fact, the simplest examples. And yeah, so I'm going to get into how to construct these. And the ultimate essence of the wide star idea is that we want to have an odd number of points that that they lead to what they're going to see. So let's say a point was here. It's going to see into this point, right? And then this, it's going to see into this point right over here, but it's not going to see into this point. So that the result is that you can kind of start wrapping around. You can create, you can maybe make something that combines these two or these two, but the idea is that you're ultimately not going to be able to combine more than two of the corners, and that's going to force convex cover up to 3. But the way we're going to do it, it's going to be that you can only have 2 hidden points. So I'm going to start by making a pentagon, and that pentagon is going to have its point. In fact, actually, I'll make this circle a little bit smaller. Yeah, that should be good enough. Now, if we make 5 gone, and we're going to rotate it so that it's really close to being in the center of that, but I don't like the way that was rotating. So in IPE, which is the program we're using, we can set the center by doing F1. So that should make sure our rotation does not leave this circle, and that's exactly what happened. So let us connect our wide star up, and let's make this black. And actually, as much as it looks cool, we want to kind of constrict this to here. And as you can see, if you want to get a convex piece, this corner over here, let's highlight it in green so those of you watching know what I'm talking about. This corner, let's change up some of the colors. Make this corner in blue. We'll make this corner, say, red. The center of this is going to be the kernel. So we can add that kernel onto anybody. So the kernel, for those of you who don't know, is the set of points which see all of the points in the polygon. So this central pentagon can see everybody. So in a decomposition, a convex decomposition, you might want to use that. You can use this pentagon with any one of the corners. And purple, we'll say, is our last one. And in fact, I'm going to just take away those axes because they're being a bit annoying. But anyways, the idea is that if you take what we call the strong visibility region of this corner here. The remaining part of the shape is just going to be, it can only see, the only parts that can see all of this are in here and in here. Now, well, I should say that if you extend this line out into here, there's still points that can see all of here, but it's not that whole corner. And so like the idea is that if you're trying to cover this whole thing, you can really only go so much into this corner and so much into this corner, or so much into this corner without sacrificing being able to cover one of these things. So that's like the intuition behind it, is that essentially what we have here is a sort of let's go with brown. This can see all of this, and this can see all of this, this can see all of this, this can see all of this. Ooh, that's pretty. I meant to just do the lines, but anyways, yeah, so this is a graph in terms of this section corresponding to this point can see all of this section. This graph happens to have independent set, so that's denoted with an alpha of this graph is equal to 2. Let's bring that up to an opaque. That's because this is a 5 cycle, and that's a very well-known graph, and you can only get 2 independent points in there. Usually click cover is denoted with a lowercase theta, and for this it is also known that the click cover of a 5 cycle is 3, right? So the nice thing is that these, although they seem kind of irrelevant, what does click covering have to do? What does graphs have to do with the shapes? But really, since these are the analogous problems, and we have a smaller subset of this issue, that implies that essentially it really implies mostly for the click cover, because the convex cover. So the idea is that this is a subgraph of the point visibility graph, an induced subgraph to be very specific, and that's very important. And there's a theorem in graph theory that states that if you have a subgraph, an induced subgraph, so let's say you have, maybe I should pull this a little bit more over, but if you have a bunch of nodes in this case, and you have some graph, right? Some random graph, right? You can take away some of these points and then what you do is you say, okay, we need a minimum click cover of this whole thing. So ignore these lines out. I did it all in one swoop, so it's going to be annoying to get rid of them. But we're going to have these nodes back in a second. So just trying to cover this section, we can have a blue click that's or red click, sorry, that is a click that's those 3, and then you have a blue click that's those 3. But they don't, since these guys don't have an edge between them, and these guys also don't have an edge between them, we can't just make it one clique. So we know that the clique cover of this graph, of the subgraph, we'll call the subgraph S, is equal to 2. It's the minimum clique cover. And if that minimum clique cover covers this, then realistically you can if you add in the other 2 points, if they could be incorporated into this clique or incorporated into this clique, then the clique cover would stay the same. But since they can't, we know that the CC of the whole graph is greater than or equal to 2. We know that, that's the theorem, but in this case, CC of G equals 3. That's the minimum clique cover you can get out of this. Well, by looking at the subgraph, we have a lower bound. It wasn't ever possible for us to get to 3, and that was because when we removed the nodes, we removed their edges, but no other edges. If you started removing other edges, then this doesn't, it starts to fall apart. But for our case here, right, we have an infinite graph, the point visibility graph. But if we just take only a couple of points and we preserve their visibility, then we know for a fact that, okay, so the theta of G is equal to 3, so that implies that the clique cover of P is greater than or equal to 3. And I mean, it's easy enough to do a 3. What you do is you say, okay, make this hexagon. Let's actually make a copy for neatness sake. Let's just take the outside, pull it down here. I can get a clique cover of 3 pretty easy. We'll just do everything in purple. Oh, nope. And nope, nope, nope. That's your 1. That's your 2, and then let's just put a random convex shape to get our 3. And that's the size of 3 clique cover. You got one down here, one up, run around here, and one over here. And let's actually do like we did last time with the dashed lines. And let's actually, I forgot to activate that. So just copy out that and then turn this into normal because I don't want the shape to have dashed lines. But yeah, so those are the convex pieces that we overlay, and we only needed 3 of them. So we're even better than this. We know that the convex cover number, which is the clique cover number of the infinite point visibility graph, we know that's equal to 3. Now is a little bit harder. Independent set has this same relationship. We know since this has an independent set of size 2 that the independent set is greater than or equal to 2, but we have to do a little bit more finagling to prove that it is 2. But it can be done easily, and there's the nice thing about the wide stars, it makes it a little bit easier to work with than our YRF example. So the wide stars, yeah, so I mentioned the origin last time, that I had been looking into these wide star type shapes in the beginning, and then I kind of forgot about them through our research of the convex cover and hidden set problems. And Eric more formally rediscovered them, and yeah, and we've been working with them, and I proved the hidden set and convex cover properties. All right, let's get going though. This shape is symmetric. It has 100 and I'm forgetting my numbers now. I think it's 105 degrees of symmetry. Basically, if you turn it 1/5 of the way, that should do the trick. So let me just recalculate that. so they don't have to put in the description. Okay, 72 actually, 72 degrees of symmetry. That sounds a little more like it. Okay. So the idea is that we can just make this, we can rotate this around, and so because of that rotation, we only really have to consider this corner. So we're going to consider this corner, yeah, so this corner right here, or rather I should say that first we start off by taking the kernel and this kernel right here, and in fact I think the kernel is a little more extensive than I'm letting on here, but we'll say this is a subset of the kernel. Magic thing about the kernel is the hidden set, number of hidden points you can throw into the kernel. Once you use a point in the kernel, you can't put any more points into the polygon. So that means, so I'll write that out. If use kernel hidden set, remaining hidden set 0 is empty set. And that's, so basically the idea is if you use a kernel, then you're kind of in dire straits. So that the hidden set would be 1. But we want to show that for all p and p, yeah, for all points in p, we'll call it a remaining hidden set of p equal to 1. So that's just me improvising some notation. The idea is that the remaining amount of points you could push into a hidden set. So if there's a point p, right, and there's a hidden set including p, there actually we don't need that equal, because we know it's not equal because some of them have 0. It has to be less than or equal to 1. And the idea is that using any point, you can only throw one more hidden point in there. So the idea is any point in here sees, well, what's called the strong visibility region, and what that entails, let me actually just make yet another copy. So that middle part is really done, but we'll make purple. Alright, so yeah, so we take that point, take these lines, let's actually group them together to make it easier. In grouping, you just do Control plus G. Let's copy this, group that. Yeah, so that's, all those points can be seen, and in fact all the rest of the polygon can see, yeah, all the rest of the polygon can see the entirety of this corner. So the visibility polygon, the strong visibility polygon of that green region is here. And the idea is that if we can show that all the points in here see all the points in here, or the remaining remaining area to be adding in any hidden points. Also, I should reiterate, strong visibility means that all of these points can be seen from this entire region. So it's a more robust way of saying that for all the points in here, if you use that as a point in your hidden set, all of this region must be, at least all of this region must be seen. So the easiest way from here to prove that the remaining region is, you can only fit one more hidden point in there, is to make a convex cover of the remaining points. And as you can see, this is a convex shape. All those angles are much less than 180 degrees. And as a result of that, we have we have the fact that if you take any of these corners, right, all the points in these corners, if you use any of them, the remaining hidden set can be at most size 1. So that means using one of these, your hidden set, any hidden set that includes a point in here can have size at most 2. Therefore, the hidden set number, because we found a hidden set of size 2 over here, being any of these independent sets, so really any 2 consecutive in clockwise or counterclockwise order, those will form a maximal hidden set. And what that does is it shows that we have hidden set less than or equal. We have the hidden set of the wide star equal to 2. And this is quite different from our previous example where hidden set and convex cover collapsed. And this is a little bit more of a complicated way of doing it. You know, finding a convex cover and then separating it out into regions. Thankfully, this one was rotationally symmetric, so we only had to do this once. But and we just applied the symmetry. So we just said, okay, kernel is special. It's always going to satisfy what we want for this these proofs, and then otherwise we just need to grab a corner and go with it, and see if we can get that the remaining hidden set would just be filled in there. And yeah, so that's the main point. Now horizons for this would include trying to make a proof that hidden set is always within a constant factor of convex cover. I believe that to be true, and it probably is pretty easy. You can string these together, and you'll get that convex cover is 3/2 compared. And yes, so I'm researching into right now, and that's going to be part of what my honors thesis. That's my senior year thing. So that's going to be part of that work, and I'm working on an exact proof for that constant bounding. But yeah, so that's the basic way of doing it for hidden set and convex cover in terms of getting those to be showing that they're not equal to each other, showing that one has to be a specific number and the other has to be a specific number when they're not the same. Like I said, much more intensive than just finding a hidden set and finding a convex cover that are the same size. Much more involved. Now, for the guarding and witness numbers, we could do similar work. So for this, I mean, for the wide stars, they're both equal to 1, but there's a shape, and I will grab a picture of it because I always forget how to draw it exactly, but I'm going to draw a picture and then trace over it. So I believe, so here's my picture, and this should be. So what we'll do is we'll get rid of the snaps, and we will draw in these points here, and that should be sufficient to make Godfrey Toussaint's. Oh, we didn't. Let's vertex snap, and yeah, this is called Godfrey Toussaint's favorite polygon. He was a computational geometer a few years back, sadly passed away, and this was his go-to polygon for numerous visibility problems. Let's just go back to angle snapping. Sorry, not angle snapping, grid snapping. And the idea behind this polygon is that your witness number can only be 1. You can only throw one witness number in here. And the guarding number, however, was 2. You need 2 to guard it. So let's actually try to use the same graph theory tactics to attack this. And I mentioned earlier that the graph power is involved with the Godfrey Toussaint polygon. So let's grab the let's just throw another point in here. Right. Yeah, so let's grab a point here, and we'll grab a point on the end vertices over here, and let's do the graph. So the graph, which we'll draw in brown, is in the power graph. So that means that they have to be min-link 2 from each other. So what that means is that this point over here, in fact I will use the spline tool, this point over here is min-link 2 distance away from here. And I'm just trying to think a little bit ahead. This is also min-link 2 from here, but this is potentially an issue. Yes, this might not be able to be done with graph theory. I've not seen the proof of why this is has to be 2 guardable. Because these are also, this will form a clique with respect to min-link distance 2. So this is a little difficult. So we may have to get a little bit more creative with this. So we just draw out this right here, and then just extend this to here. I think this is going to become a trend with these shape times. That I'm going to encounter something that I forgot how to do, and then the next one I'll look it back up and I'll be back to the races. But so this is that share. This is what this point can see, and then I'm not even going to the right point. Yeah, I don't want to use the polygon tool. I just want to use the polygonal chain tool. yes, so I mean, if you look through here, you can easily tell that these points are not going to be all able to be seen from this same central point. So perhaps instead of looking at a clique in the square graph, we can just try and show dominating set, which is another equivalence of the guarding problem. Show that there's no way of there's no dominating set for this. That actually I think is a better tactic. However, it's possible. Yeah, so we actually can't use the graph theory for that. That's the problem with the graph theory, is that the ultimate trade-off, right, is that the graph power will draw the lines willy-nilly for when they're min-link 2 away from each other, but that doesn't mean that all points that are min-link 2 away from each other are min-link 2 in the same way, for the lack of a better term. From those same points. I'm just thinking a bit. But that is how it works, though. That is exactly how it's supposed to work, at least. So I may not just be thinking terribly straight about this. So we're going to grab this point here and this point over here, and we're going to pull this out to there. And so as you can see, there's these little common areas, and that's what is causing, quote unquote, the issue. And that's how you're going to show that the witness number of this can be no greater than 1. Is that, yes, okay. Yeah, so this is probably not going to be best served by the graph theory, because everything in here is every point in this shape is min-link 2 away from every other point, I believe. Yes. Yes. Every point, yes, so the power graphs get a little bit more complicated. But however, so that's the, yes, that gets a little interesting. So each of these points, yeah, so they're each min-link away from each other too. But they are not. Yes, this gets a little complicated. But the idea is that, okay, if you use any of these, you do this strongly visible region, if you use any of these, you can't use any other point in the entire polygon. If you use a point inside of, so these are rotationally symmetric, but if you use any point in this cubby, it's going to go out to there. If you use, or even if you use any point in this entire region, the strongly visible region of this entire region is equal to itself. So that rules out this being used. You can, if you try to add anyone else in, then you won't, and then you show that by doing the star-shaped polygon. So let's just actually show it how we did before. Yes, now I'm hitting my stride. Okay. So, and then we do our pink polygon. It doesn't have to be a convex polygon, it just has to be a star-shaped polygon. Which means that as long as everything is visible from this point, we are golden. So let's say all these points can be seen from there. And as you can see, rotationally symmetric, you get everything except for this little small triangle in here. And then what you do for that small triangle is the same idea. This strong visibility region of this whole triangle is like this whole entire, is at least this triangle. And then you and at that point it's not a matter of covering it with a star-shaped polygon so much as ruling out that you can use these points over any of the points in here. So you wouldn't be able to use a star shape to rule it out, I believe. But there's no star-shaped polygon that sees all of these points. Yeah. So yes, my theory going into this video was wrong. We can't just use some basic graph theory to fully prove the point about the Godfrey-Toussaint polygon. But we definitely can use it for hidden set and convex cover. That's the way to do it. So another failure, I guess. But at the end of the day, like the point remains. You can only throw. Once you use any witness point in here, it becomes impossible to use any of the other ones. And if you use one on the inside of this, well, then it almost becomes obvious you can't use. You're forced to just use all these ones. So it's impossible to. And in fact, I was doing a disservice by showing the star shape, because that would have only proved witness point 1. Sorry, it wouldn't show the witness point 1. It would show witness point less than or equal to 2. So yeah, so that's just my little. That was a nice little geometry talk, shape time. And if you have any questions, don't hesitate to throw them into the description. As I was saying, this is more casual. I just walk through some idea and I just try it out. And if it doesn't work, then I think about it and I come back next time and I correct my mistakes. So this is correcting my failure to produce the non-homestead. I was just getting caught up. I forgot that these circles have to well, the point, the whatever, it has to be an odd-sided figure. On the inside of this, it just has to be smaller than just has to be wholly contained in it. And what that begs is the natural question becomes, and I doubt that this can work, whether it can be done with a triangle. I suspect it can. Well, let's make the triangle first, using our regular Pentagon goodie. And then what we're going to do is we're going to take an in circle of that triangle. We can make it a good bit smaller too. Goodies, another I don't want a parabola. Another goodie, another regular Polygon, and we're gonna just rotate this to be about. Once again, I have to do my center. Rotate this to be about the way. And then we go like that. And this actually, I may have discovered something on the fly here. Let's just get rid of these. Oh no, I doubt. No, I'm not that clever. This, or am I? This actually would exhibits the properties of so the hidden set. These are both hidden from each other. Problem is, convex cover of this is going to be 3. So yeah, this is the simplest wide star. And in fact, when I give my talk, I will use this as my other example, because this is the most elementary of the wide stars. And the idea is that we do that same proof walkthrough, except instead of having a pentagon in the center, we have this nice little triangular kernel. Let's make it in a more noticeable color. Like what we're doing orange, with dark orange. The idea is, okay, any convex piece will have that. The click cover. So none of these all. Yes, okay, I see. Yes, I may have been hasty with this. Okay, but that's, once again, the idea of these are to be a little wrong and then prove yourself right. The problem with this is that it has hidden set size of 3. So this point is mutually invisible to both of these. And then you grab. Yes, so if you grab these and pull them down, you get that strong visibility region like before, but you can't connect these up. So that's the essential issue here, is that we're trying to do we have to get to a 5 cycle or larger. And that makes more sense with the perfect graph theorem. Basically, if unless it has a cycle of 5 or larger, an odd cycle of 5 or larger, then we're not able to get this what we call perfection. So if it has those, then if it has a 5 cycle or larger, then it's an imperfect graph. And any polygon which has a perfect graph must be a Homestead polygon. So this one has a perfect graph because you can't get a 5 cycle out of here, either in hiddenness or in visibility. But it doesn't matter which way we go. So I was wrong. I did not discover anything on the fly. So the idea is that because we have these 5 points in here and they form a cycle in visibility, it's possible for these to diverge. But since this is only 3, it's not possible for these to. So this is a hiddenness cycle, but if you try to add in any intermediary points, like this is going to see into there. If it's like in this pocket but can see both of them, then it'll create it won't create a 5 cycle. So any point, that one would have to be a point over here. It doesn't see it, so that would go 1, 2, 3, and this, let's pull it over. Nope. I always accidentally hit the A key. It was like over here or something. It was something that could be seen. Well, that one would probably be seen by that one, but let's do our boundary. Do it like that, and then let's just pull this even further down. Like that, so it just has to be below that. And what this would be is actually 1, 2, 3, 4, and then there'd have to be something over here to complete the cycle. That's a 6 cycle. That's not a 5 cycle, and hence our problem. So there's no odd cycles of size 5 or larger in here. We can go more exhaustive with that, but because of that, it's perfect perfect polygons are a different thing. It's when it's the witness number and guard number, but homestead polygons, it can't be a polygon. It's a polygon with a perfect graph, therefore must be a homestead polygon. Yeah, so that's why wide stars with less than 5 points of the star, or with less than 10 vertices, they're not possible. The 4, if you try to do it with quadrilaterals, then you don't get that 5 cycle we're talking about. You get a 4 cycle, and a 4 cycle is perfectly legal for perfect graphs. So that's still going to be a perfect graph, and it's still going to be a homestead polygon. So I hope that you enjoyed this discussion, and that little failed innovation down there. And yeah, hopefully I can show that this is the bound. I do actually believe that this is as good as you can get. Yeah, and yeah, hope everyone has a great day.